All right, so let's start. Thanks everyone for joining us today. I hope you all had a great week. Today we have the pleasure to host James here, who is a postdoc at Vector and a visiting researcher at Mila with Joshua, and he'll be sharing some thoughts with us on LLM processes. So before handing the mic over to you, James, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, you just have to raise your hand and wait for me to give you the mic so that people online can hear you. And for people online, you just have to say, I have a question or question in the chat. And when the time is right, I'll let you directly ask it. There'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with James. That's pretty much it for me. So whenever you're ready, James, floor is yours.
Yeah, thanks very much for having me, and thanks for hosting me. I'm pretty excited to talk about some recent work that we've done on LLM processes. It's going to be at NeurIPS in Vancouver if anyone's going. Yeah, so let's get started. Please, if you do have questions, we'll keep it informal. Feel free to ask. Please stop me. So part of the inspiration for why we did this work is we kind of looked at classical probabilistic regression and some of the shortcomings that we felt that it had. So first, some of the positives. It natively handles numerical data. It has fast inference and predictions, and it usually gives closed form predictive distribution. These are all good things about classical regression, stuff we'd like to have. But some of the problems are if you want to incorporate any side information, anything like expert knowledge, high-level observation, if you have any side docs, you want to include any data from relevant tasks, it's really difficult to incorporate this information into your predictions, right? Usually you have to use some closed form mathematical priors, or you have to really carefully engineer the type of model you're going to be using so it has good inductive biases for your task. You need an expert to be able to do these types of things with classical regression. If you have any missing values, or you often have to figure out a special way to handle that. And incorporating of context, it doesn't know anything about any side information, right? Unless you explicitly tell it. On the other hand, we've seen from LLMs that it's really easy to attach side information in text. Just do it in context. You can chuck it in. It automatically handles special or missing values. You don't need any special assumptions for that. And you can automatically, this is a bit hyperbolic, right? But you can automatically condition on the entire history of the world, right? We have all the training data from the internet. In some sense, it knows about everything. So if you want to condition on any previous knowledge, you don't have to do anything about it. But now, if you want to use LLMs for regression, there's obviously a lot of things we have to overcome. We need to tokenize and detokenize numbers, first of all. That's kind of a bad thing. It's generally slow, right? These models are slow and expensive. And it's not clear on the face of it how to create a distribution over numerical values, right? We have to take a distribution over tokens for natural language, and we're going to have to convert it to a distribution over numerical values. And so in this work, that's what we did, right? We tried to overcome some of these shortcomings, and we wanted to generate LLM-powered probabilistic prediction. So we built a model that basically allows you to talk to the model, to give it text, give any context that you might have in natural language, and incorporate it into the probabilistic regression problem, and harness the massive latent knowledge that's in state-of-the-art LLMs. So here's a little demonstration of what the model is going to look like. So let's say we have these numerical values here that we want to show the model. This is going to be our numerical context. Here are our training points. And above, I'm going to display some text that I'm also going to give to the model that I wanted to condition on. And so I'm going to display the text, and it's going to produce the probabilistic prediction in this graph here. So as I'm telling it the text, it's updating its predictions. I'm going to say this is a financial time series, so it's going to condition its values to be above 0. I'm going to say that the company goes out of business, where it makes the prediction go to 0. And then I say the stock goes to 0 on day 30, so it conditions on that fact, and it makes the stock go directly to 0. So this is the kind of thing we want to get out of it, right? And we're going to talk about how we did this. So the model we called LLM processes. And so to get the best of both worlds of probabilistic regression and LLMs, we want a model that defines a joint distribution over numerical values and unstructured text, right? We want to be able to condition on both numerical values and unstructured text in green, numerical values in blue, and we want to produce a probabilistic regression, a probabilistic prediction over the numerical values in orange. Now we know an LLM is a natural model for doing this because it handles the text quite naturally. But how do we get an LLM to express a complex joint distribution over the numerical values? So let's first talk about the various ways that an LLM could represent a number, right? We know that an LLM's output is text. And let's pretend we said, like, we think that the LLM is trying to say the number 50.318. What are the various ways that it could do that? So we have all these numerical representations that it could use, right? In text, it could say like 50.318 as a string, say 5.0318 times 10, et cetera, et cetera. And why we might be concerned with this is because if we think that there's some inherent knowledge that the model might have, and we think that that's going to be good for regression, we might want to collect all these various ways that the model could be communicating to us the various values, right? We don't want to discount any of them. But on the other hand, it can get a little bit hairy, right? So it could be saying 50.318. It could be using ASCII art. It could be using binary. It could be using some crazy, like, who knows, right? These are all the various ways that an LLM could be communicating this value to us. And we're going to make our lives easier if we're able to, you know, limit our potential things that we're looking for, right? It's probably impossible to grab them all, so we want to limit them. But it's an empirical question as to how good it's going to be at probabilistic regression if we start cutting some of these out, right? We want to say, like, if I do this, I'm actually going to damage my predictive power of the model. Now, unfortunately, we use them in this work. We use the not very exciting, like, just decimal representation, right? We tossed all of these out and we said, okay, I'm just going to assume that my model is going to feed me the decimal representation of the number that I'm looking for. And perhaps we can use some prompt engineering to make it a lot more likely that this is actually the value that the model is going to give us. It's not going to give us some random ASCII art, okay? So that's the principle we're going to use going forward. And we're going to use two types of methods for eliciting the numerical distribution. We're going to use a sampling-based method and a logic-based method. I'm going to describe both of these. So far, so good? All right, cool. All right, so let's say we have this data set here. I want to condition on these three values, and I want to make a prediction at the index x0 star. So what we're going to do is we're going to take all these numerical values and we're going to convert them into a string. And what we're going to do is we're just going to list them out, convert them into a string using our decimal representation that we agreed we're going to use. We'll separate each value by a new line, or sorry, each value by a comma and each tuple by a new line. And at the very end of my prompt, I'm going to put the index that I want my LLM to predict at. I'm going to shove this into an LLM. And we know that LLMs are next token sequence generators. So I'm going to assume that the LLM is going to be completing the sequence that I'm prompted it with, and it's going to actually put the next value for that index because that's what I've prompted it with. And I'm going to use rejection sampling, and I'm going to say if this output it gave me, this y0, doesn't adhere to the numerical representation that I'm expecting, I'm going to throw it away. So if it gives me some random strings or whatever, and it's not what I want, I'll just toss it. If it does, then I'm going to use it and I'm going to toss it into my collection of samples. And in doing this, I'm going to generate an empirical probability distribution over values y0. And so I can do that independently at each of these target locations on the x-axis here, generate a bunch of samples by repeatedly doing this procedure. And I can generate a predictive distribution over all of the y values that I'm looking for. The procedure makes sense? It's random sampling, exactly. Yeah, it's random sampling from the LLM. Yeah, that's right. Okay, so the second way that we're going to elicit a predictive distribution, we call a logic-based method. And this is going to be a lot cheaper, especially if you want to just know the log likelihood of a particular value under your model. So let's say I have one value and I want to say, well, what does my predictive distribution say is the likelihood of this one value? So let's say that value is 325. So the way that I'm going to define my likelihood of 325 is I'm going to say, okay, I'm going to look at the probability of the string 325. And using the autoregressive likelihood of LLMs and the product rule of probability, I'm just going to decompose this string and say, okay, the probability of the string 325 given by my LLM is the probability of the token 3, and then the probability of the token 2 given 3, and then the probability of the token 5 given 2 given 3, right? This is what an LLM would do. Yeah? You look not convinced.
It's not that I'm not convinced, but I wonder if the API is giving you the way to query this. Like when you use the API for GPT, say, can you ask like, what's the likelihood of this token being the next one? If it's part of it, then that works.
Yeah.
If it isn't, then it doesn't really work, right?
Yeah. Well, if you have if you don't have an open source model, if you're using like the API for GPT used to allow you to look at the logics for tokens. They've kind of closed that feature now. So you're right. You'd have to use the sampling based one. You couldn't use that one for this. But all of the like Hugging Face open source models, you can do this with them. Yeah, good question. Yeah.
Thanks. So I guess these logic probabilities are not like perfectly consistent with the sampling based one though, right? Because you're like, how do you mimic the rejection sampling thing here?
Excellent question. Okay, so I'll return to that actually. Cool. So how do we actually look at these how do we compute these likelihoods, right? I talked about you can look at the logit of 3, but if I do that just by default, it's actually the probability of 3 given any token that I could have in my entire collection, like my entire dictionary, right? But I want to restrict it so that matches the rejection sampling. So I want to restrict my corpus of allowable tokens to just be the numerical ones. So I'm going to actually have to look at the logic for the value of 3, and I'm going to have to renormalize my distribution. And this procedure will actually mimic the rejection sampling that I was talking about earlier, right? And so if I look at the probability of the token 3 and I normalize by my numerical values, I can interpret this as the mass that the model assigns between the values 300 and 400. Can you guys see why that would be true? Because any value that is between 300 and 400 must start with the token for 3. So anything that follows that, right? This is going to collect all of the mass that's in that bin. So it's going to look like this. Right? This value is going to represent all the mass for all values that LLM assigns between 300 and 400.
Why not between 3,000 and 4,000? You don't know how many digits are.
Oh, you guys have good questions.
Okay.
Hold on to that too. Good. All right. And so if we keep going down the line, right, we can look at the probability of the token 2 given 3, normalize again, with an asterisk, the probability that the model assigns between 20 and 30, given that the first digit is 3. So this would look like this. And continue down, same thing. And so we sort of get this infinite resolution if we want, like as fine as we want. We can zero in on the exact bin we want, right? And actually calculate the probability of the value being within that bin. But as Guillaume points out, there's one problem with this. Let's say we have the value 3,254. Again, we decompose this and we notice that necessarily by what we're saying, the probability of 3,254 will be less because it contains one more term and all these terms are less than 0 or less than 1, right? And so we need a way to establish the order of magnitude. As Guillaume said, we don't know if that first 3 represents 3,000 or 300 or just the value 3. So we just need some trick to toss in to say, like, I'm actually going to be looking at this particular order of magnitude, right? And so the way that we handle this is we say, if we're going to look at the likelihood that the model is outputting 325, we need to introduce some terminal token, something that lets the model know, okay, now you're done. you're really looking at the value of 325 and not the value of 3,254. And so when we put the terminal token in as the last term in this product, it guarantees that this wasn't talking about 3,204. Okay. Still some skepticism, but
it feels so convoluted. So you'll have to convince me that this is better than the rejection sampling, because the rejection sampling method sounds good.
yeah, it's intuitive. It's great.
Worse than that, because this feels convoluted.
Okay, so let's talk quickly about some pros and cons. So why would you do this instead of the rejection sampling? The rejection sampling, it works super well. The one reason you might want to do that is that the rejection sampling is expensive. So to get like a value, let's say you have some value and all you care about is like the log likelihood of a test set. If you do the rejection sampling, you have to form an empirical distribution, and then you have to find some way of actually evaluating the log likelihood of your value under that empirical distribution. So you have to fit like a Gaussian to it, or maybe some kind of mixture model to your samples. And then you have to say, okay, now that I have that, what's the likelihood of my value, right? And there's going to be some error there. So this is getting around that by saying, like, you only have one value. Tell me what the probability of my value is under my distribution. That's what this is doing. And if that's what you care about, it's way cheaper and way more accurate. Okay. But now you bring up a good question, which is like, well, what about these two methods? Are they even the same, right? They were the same before when I said, like, I can match the rejection sampling by renormalizing, but now I've introduced this terminal token. Does this even represent the mass, like between 325 and 326, the way rejection sampling did before? Right, that's a really good question. Does this even line up with the rejection sampling technique?
James, I have a question online.
Yeah.
Tegan is asking if the logits are somehow only over numbers. Don't you have to also normalize over chars and other tokens?
Yeah, so I kind of swept that under the rug and I put like 0 to 9, but any allowable token in your rejection sampling technique, you'd have to include in that. So for example, we're going to toss this terminal token in, and we're going to toss like a decimal to represent the decimal point. That's a good question. And also a caveat is this sort of decomposition is nice if your LLM uses an individual token for each number, right? But some LLMs do weird stuff like, you know, take the number 32 and tokenize that as an individual token. And that really messes this up. So the nice thing is these models I've listed here use individual digit tokens. So that makes our lives a lot easier. If it doesn't, you can kind of hack it by like injecting spaces between values so that like it tokens them individually. But again, it's not exactly clear like what that's going to do to the performance of the model. But now the question of like, okay, sampling versus logic-based distributions, do these actually give you the same thing? We did some like, you know, empirical experiments to see like, you know, if we could satisfy ourselves that these two distributions actually gave us, these two methods actually gave us the same distributions. And to our satisfaction, we found like, yeah, they're very, very close. So this is a visualization of the rejection sampling technique, the predictive distribution. The highlighted values are the training points. And then this is just a visualization of the heat map of the predictions. Whether you use logic or whether you use samples, you get very, very close distributions. Yeah.
Just a follow-up. She's asking if you end up with numerical issues since you have to normalize over a large vocabulary.
We have, okay, just on the face of it, we haven't encountered any numerical issues. The thing you have to normalize over, you do everything in like logit space, like in log probabilities, so that helps. And you only have to normalize over a small collection of logits because you basically mask out everything that's not included in your like allowed tokens. Yeah. So at any rate, we haven't encountered any numerical instabilities due to that. Okay, so I've talked about the methods that we're going to use to elicit predictive distributions. We can sort of use a bunch of techniques to take numbers and convert them to strings. What's the way that we should do this, right? We kind of did some experiments, some prompt engineering to see like what's the best way to actually convert our numbers to strings to get the best results from an LLM. So here's kind of like a user guide from what we found works best. So let's say we have these values here, these colored values, and we want to make a prediction at 2.7. And how am I going to create my string? There's lots of different ways that I can create the prompt string, right? So I could just list all the values separated by a comma. I could list all the values separated by a comma, and I can put a new line between tuples. I can do that, but inject spaces. I can use brackets. I can put X, Y values. I can be super explicit and just put X equals blah, Y equals blah, 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 blah. And we found in our experiment that just separating by a comma and using a new line, this is a good balance between performance and token efficiency. So obviously we're up against like memory constraints and token limits. And so we found like this is a nice concise way of encoding our data set. It works quite well, and it's not super heavy on wasting tokens. And we sort of hypothesized that, it's basically a CSV, right? I'm sure LLMs have seen like a billion CSVs, so it makes sense that it would like this way of formatting it. Yeah. Yeah, good question. Okay, I'm gonna come back to that too. Yeah, because text is super flexible, right? No, the question, sorry, where the mic was, are we just concerned with 1D? And no, we're concerned with multiple dimensions. Okay, now the other question is, this is order dependent, right, on your conditioning set. So which way should we put our training set into our LLM to get the best results? And the way that we've found works best is to order the data so that you put the closest training value to the target at the end of the prompt. Sorry, that's a word salad. Let me show you visually. So we're going to make a prediction at 2.7. I'm going to look over my training data. I'm going to say, what's the closest value to 2.7? It's this orange value. I'm going to put that last. Then I'm going to go through. I'm going to say, what's the next closest value? Put it before that. And my farthest value, I'm going to put it at the very beginning. And again, we hypothesize, right? This is doing, like LLMs have some kind of attention. Presumably, they place higher weights on context that's closer to the end of the sequence. We found it works better if we put the relevant, there's some kind of like, if you were to build a kernel with like a Gaussian process or something, you'd have some like distance relationship, right? We assume this is mimicking that. I mean, that's a good question. I actually think that might be worse, and also that's super expensive. But if you permute it and take an average, at least that's permutation independent, right? So that would be a nice property. Yeah. Just permute it. Yeah, it's a good question. Yeah. But at least if you have to choose one ordering, this is the one I would use. We also looked at Y scaling. So what if you took your Y values and you scale them like either down between 0 and 1, or if you scale them up, like does this actually affect performance? And we found, yeah, it does. So performance degrades if you increase the magnitude of your Y values, it gets worse. If you incorporate negative values, it's also slightly worse. But this brings an open question that we weren't able to investigate in this work, but which is, we're going to eventually get to incorporating text, right? I told you, like, this is the big selling point. I want to incorporate text in regression. So if I'm going to incorporate text, is it actually better to leave my problem in its native magnitude than to mess with it? Because you're going to be destroying information if you do that, right? So let's say you have like some problem which is dealing with, temperature, and you scale everything between 0 and 1, the model will be like, what are you talking about? So we didn't get the chance to look at that, but it's an interesting question. And we looked at top P and temperature, and performance was actually surprisingly insensitive to these, we found. Okay, cool. So the whole point was we wanted to define a joint distribution, but everything I said was how you make predictions at a single value, right? And so to make a distribution over all values, so far all I've told you is that you can do it independently, right? You can like break up all the values and do it one at a time, and you can make predictions there, and then you get a joint distribution. But all of these values are conditionally dependent from each other, right? Conditionally dependent given the model parameters and the context set. I haven't actually parameterized any rich structure between the values, but I want to parameterize a nice rich joint distribution. So how can I do that? Well, I can take inspiration from autoregressive models. I can take inspiration from LLMs, and I can say, well, if I'm going to make a prediction at multiple values, why don't I make a prediction at the first value take that value, plug it back into my LLM, and do things autoregressively. So now if I need to make a prediction on my second value, I take my first prediction, I put it back in, I pretend it was part of my training set, and I make a prediction at the second value. So this is just decomposing the joint distribution autoregressively, right? Again, using the product rule, just like an LLM would do. And that induces a joint structure over all of my predictions. Now, this has some pros and cons, right? So the first way I parameterized this was order independent. So it didn't matter the way that I saw my test points because they were all independent. It didn't depend on the ordering. And so this actually defines a valid stochastic process. Now, why would we care about that? Well, we might care about getting unlucky with the way that we're ordering our test points. So if we think like, oh, if I do my test points in a certain way, I'm going to get a really bad value, right? That might be one reason that we're concerned with that. And this way, parameterizing it autoregressively, this now becomes order dependent. I have to choose an order to roll out my predictions, and then I have to do it autoregressively. Do these two concerns make sense? Yeah. I'm getting so much. Everybody's good? You guys good? Yeah? All right, cool. All right, so should we be worried about output ordering? So some questions we could ask. Are independent marginal predictions actually worse than autoregressive ones? Do we even care, right? Do we need to worry about getting unlucky with our output ordering? I already mentioned that one. And is there a particular output ordering that we could use to improve performance? Okay. All right, hope you guys aren't getting tired with strings, because here we go, we're gonna do another one. So how do we wanna make predictions at 0, 3, and 4 given this test set. How are we gonna make predictions here? So I'm going to propose a method, which we call, we're just gonna say like context ordering, and I'm gonna predict the target point, which is closest to the context set. So I'm gonna look at all my test points, and I'm gonna find the X value, which is the closest one to my entire training set. So in this case, it's the value 3, right? Because 3 is the closest to 2.5. It's gonna be the first prediction that I'm gonna make. So now to make this prediction, again, remember, I'm gonna order my training points, again, from farthest to closest to 3.0. I'm gonna predict my value at 3. And because it's autoregressive, I'm gonna add this back into my string. So I'm gonna assume this was a training point. Then I'm gonna make a prediction at 4, because 4 is my next closest X value. I'm gonna take that prediction, plug it back in. Notice that I've sorted my training points, again, from farthest to closest to 0. 0 is the next point, and I can make the prediction there. And I just repeat this procedure. So basically, I'm sorting both my training and my test by closest to the prediction that I'm trying to make. And so here's an experiment that we ran to see if any of this mattered. Okay, so first question we want to answer: are independent marginal predictions worse than autoregressive predictions? The answer is yes, they are. Okay, so the independent predictions are this is log likelihood. Independent predictions are the X values. And you can look at the little blue circles. Those are autoregressive predictions. Okay, so do autoregressive. It's better. Are we going to get unlucky with ordering? The answer we found empirically is no. So if you look at the error of these random tests, these are random orderings. We found that the variance was quite small, no matter what the ordering we picked was. So you don't really have to worry too much about picking a bad ordering for your output. It's going to be fine. That's what we suggest. And should we use the method that I described at the end there about ordering our test points? We found some, I would say, weak evidence for yes. So the purple circle there are the sort, if we sort our test points. You can see sometimes they're below the random orderings, but generally they're above, or at least as good or above. So we would suggest that as a method for actually producing predictions. Yeah? All right, cool. So thanks for sitting through that. Now you guys know how LLMPs are going to actually produce their predictions. Are these things any good, right? So we evaluated it out of the box, right? We just applied them as a numerical regression model. We compared it to Gaussian processes, and they were competitive, which was super surprising to us, like that you could just like, this is no training, right? These LLMs are not trained. They're just pulled off of Hugging Face and applied, given in context these test points, and they're actually competitive regression models. I don't know, that was crazy to us when it's less crazy now because we know all the stuff LLMs can do, but at the time we were like, what is happening here? I'll skip through this. So we did some experiments on Bayesian optimization. They work well for that. And interestingly, they're flexible regression models. So they give really, because of the way that you're parameterizing the predictive distribution, they give really wild predictive distributions, right? So they're multimodal, as you can see. Like if you take a cross section, there are a couple of modes here, and you can see some weird artifacting around like integers, right? You might expect LLMs are like biased to like put in integer values, so you can see this weird banding effect. But it's, I don't know, it's pretty interesting to see like what does an LLM think the predictive distribution should be. That's it. That's what it looks like. So LLMs can easily handle missing data, which is a nice property, right? If you think of the way that we are taking our numerical values and we're plugging them in, we don't care if any of the data is missing because we just put it into a string and shove it in, right? And earlier there's a question about, do we care about only 1D experiments, or can we handle multiple dimensions? And yeah, we can handle multiple dimensions because we can encode multiple dimensions in the exact same way. We can handle a joint distribution over any subset of variables. So let's say I have this collection of data, which has 5 variables here. And I want to condition on some subset of it, and I want to predict some other subset of it. So let's say I want to model the variables C and E, and I want to condition on the other variables. All I have to do is I have to arrange my prompt so that the variables I'm conditioning on come at the beginning and the variables I'm predicting come at the end. So I can use an LLM to model any collection of variables, any dimension I want. It's a super flexible way of modeling, doing regression. So we did some multi-dimensional regression experiments as well. So here I'm simultaneously predicting temperature, precipitation, and wind speed in London using an LLMP. And again, it's competitive with Gaussian processes. And here I'm actually using an LLM to do image completion. So I'm encoding pixel values as XY and then intensity, just plopping it into a string and getting the LLM to complete the sequence. And I mean, it's not super crazy impressive, right? Like there are models that will obviously do a lot better than this, but this is just like, you know, a proof of concept that an LLM can actually do like reasonably well at image completion. I'm gonna skip this. Okay, so that's all great, but like none of this was particularly amazing at regression, right? Like, you know, if you wanted to do regression, like just numerically, I would probably say like an LLM is expensive. It's like not the best choice. So why would we do all of this? What can we do with LLMs that we could, or LMPs that we couldn't do before? So one potential interesting application is we can now condition on side information, right? So let's say we like have a big CSV with all these values. These are all data from housing prices in the US. So, you know, we have like addresses, we have square footage, we have number of bedrooms, blah, 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 blah. Some of it is text, some of it is numbers, and we have some missing values that I want to predict. So what I could do is I could just like make a string out of one of these rows. That string contains text, it contains numbers. I don't care, I just shove it in. I can pass this to an LLM, and I can get the LLM to make predictions at the locations that I want. And I can fill in those values with uncertainty, right? There's like a lot of like methods you could use for filling in a CSV. A lot of them are point estimates, but this one gives you uncertainty estimates and also can condition on any of the text that you have in your CSV as well. So now the question is like, does any of that text actually help you compared to the numerical values? So we ran an experiment to predict US housing prices, giving a training set of only 10 examples. And so on the left, I have all of the numerical values that would be used, that would be given to the model that it has to predict the housing price from those numerical values on the one hand, okay? So on the one hand, I'm going to give an LLM that object on the left, and I'm going to ask it to predict the price of a house. And in case two, I'm going to give all of those same numerical values, but I'm actually going to give labels to the values. So I'm going to say, this is the zip code, this is the population, this is the number of rooms, et cetera, et cetera, et cetera. So the same, exact same experiment. It's got 10 in-context examples it can learn from, and it's got to predict the 11th example. And the question was, does actually adding any of that text help in your regression problem? And so here are the prediction without text labels. So this is, again, an LLMP. It does reasonably well, right? So it actually gets more or less like within its uncertainty bounds. It does pretty decently. There's some like are outside there, but that's not too bad. But when we incorporate text, we can see that we actually do improve the predictions quite a bit. So we're able to narrow in on the values. We're able to shrink our uncertainty bounds, and we're actually able to do much better predictions. And if we look at on aggregate, so we repeated this procedure several times, and we looked at some error metrics in aggregate, and we see that, yeah, we do improve in terms of performance metrics. So is this clear what's happening like in this experiment? Yeah.
I wonder if you've also just compared to if we were to actually run a regression model, like if we were to take those same numerical values, give it the 10 points, how does that compare to just doing a regression?
Yeah, so it's a good question. We sort of, my gut feeling is not very well. Like we should run it, it's true. But we sort of like formulate the experiment to be really difficult for a standard regression model, to only get like 10 training examples. So like, depending on like, you could use like maybe a linear model that might do okay, but anything that's like really over parameterized, I feel like would just overfit to that like crazy. And yeah, it's a good question, but I anticipate not very well.
Yeah, I guess because there's such a cost difference between doing the two, that seems like a really strong incentive to, that would be like the trade-off between performance and cost seems important here.
Yeah.
And so that would be something important to understand.
Yeah. So, well, we submitted some work to iClear with ServiceNow. Like I was a collaborator on a ServiceNow project where we made a benchmark, which was actually incorporating text into time series forecasting. And we did in those experiments compared to like vanilla regression models, forecasting models. And the performance gains, we looked at like cost versus performance. And it's like, it's going to be a question as to like, the user, what they care about. But you did get like a lot of performance gain by using an LLM and incorporating the text versus in those experiments, for example. Yeah. So if you can pay the price and you care about that extra like bit of performance, it's definitely worth it. But yeah. And so another trick that LLMs can do is they can learn from similar problems in context, right? And so we wanted to see, could LLM processes do the same thing? So for this experiment, what we wanted to check was we wanted to see, we're going to give the model 4 observations of monthly precipitation at various locations across Canada. And we're going to ask it to predict the next 32 months. Okay. And again, we didn't look at other regression models, this is just LMPs, but basically it gets to see these 4 and then it has to predict the rest. So again, a very challenging problem, right? And you can see when we just do that, it usually predicts like maybe the expectation or like kind of just biases towards 0. The predictions are not very good. It does what you would do kind of like you'd expect. You just like draw a straight line from the values you saw. But then we wanted to ask, well, what if I show it previous 36-month historical observations from the past, from the same location? So I say like, from this place, here are 36 months randomly selected from the past, monthly precipitation values. Could it learn from those historical examples? And we did this from 1 historical example to 10 to see what happened, basically. And so if we show it 1 example, you can see it improving its prediction, 2, 3, 4, and by about 4 or 5 examples, it kind of plateaus. It's able to pick up on any seasonality in the problem. If it's there, if it's not, it kind of like gets a much better expectation. It is using the historical examples from the past. And so again, we can return to our original experiment that I showed you first, where we're putting in text and we're asking it to condition on that text to give us various forecasts. And so we want to see, like, does this work with, what if we took the same data point and we told it it was a different scenario? So we take those 2 data points, we give it no prompt. That's kind of its prior prediction, given no text to condition on, the first plot on the left. And then we tell it, okay, these are actually daily temperatures from Montreal in January. And if we tell it that, then, you guys have been here, like moves all of its mass below, like basically below 0, and says, yeah, it's super cold in January, so here are your temperatures. If we change it to May, and we condition on that instead, moves everything, makes it much more reasonable. And the bottom 2, I wanted to find monthly precipitation on Earth where it had the most seasonality versus the least. So I chose 2 locations, Singapore versus San Diego. San Diego has a really strong seasonality, and Singapore has one of the least seasonality on Earth. And I told it it's these locations, and these are its predictions given those 2 conditioning. So it is listening to what we're telling it, right? It's actually conditioning on that fact. Yep.
Just so I understand, it's only being conditioned on the text that says it's in San Diego, and that means that somewhere in its data set, somewhere it's seen these kinds of time series before?
Yeah, it's conditioned on that's in San Diego and these 2 points, that's it.
Okay.
So yeah, those 2 numerical values and that text. Yeah.
Did you know that this kind of data was in the training? Okay.
Yeah, no, I just assume it's seen everything, but yeah, exactly.
Cool, thanks.
Yeah. So that's another thing. It's an interesting tool for querying the information that's actually in. You can do counterfactuals. You could say let's say I had a house and I wanted to renovate this room, or I wanted to build an addition. What do you think would happen to the price if I did that? And see what the model says, right? All right, so let's return to this table, and here I'm going to sell you on the fact that yes, we've got our peanut butter and jelly. We've done it all. Okay, so before we had these downsides where we needed to tokenize and detokenize numbers. Okay, yeah, we still have to do that, right? We haven't solved that completely, but now we've at least stress tested some numerical encoding schemes that we found work pretty well. It's still slow. This goes back to your question, but in certain cases where you want to condition on text, we think it's worth it. And we've shown how to elicit arbitrary complex numerical posterior distributions using the output of an LLM. So now we have a method for doing that. And then the nice thing about the next 3 points is that they just inherit them from LLMs. It's easy to attach side info, automatically handles missing values, still conditions on the entire history of the world, right? All right. Now, along with LLMs, LMPs inherit some of their drawbacks, as we know, right? So there's the computation, there's context size limits, especially with open source models, any potential for abuse. So if you're, using them to forecast, ask it to forecast someone's potential for defaulting on a loan or whatever, any biases that are in your LLM, they'll be reflected here. So all those issues are still present. But we kind of view this as, one step in kind of unlocking general multimodal probabilistic regression using LLMs. So the nice thing about text is an incredibly flexible encoding mechanism, right? You can basically take any data set and convert it to text. You can give it to an LLM. And as we know, more and more modalities are being hard-coded into LLMs as well. So better ways of encoding images or videos, et cetera, et cetera. So here's a little cartoon of what we think would be cool is you want to make a prediction for housing prices when you should list your house. So you got a picture of a house, you have that data set I showed you earlier, you had your real estate agent do a walkthrough, just chuck it all into an LLM and be like, give me the probabilistic predictions for this, and then have it go to town, right? Kind of our vision of the future. And a lot of research has gone into emergent capabilities of LLMs. As you scale these things up, you can see it, all of these unknown things that it can do. All of a sudden, we've discovered that they can do it. And we kind of view our work as like adding a little tiny branch to this massive tree, where we think probabilistic regression is now we see that it can actually do that, right? So maybe in some of the time we have left, one thing that could be cool is if you guys have any ideas of what we could work on next. So as I mentioned, with ServiceNow, we developed a benchmark for looking at time series forecasting that evaluates how well they're actually using the text. So in that work, we tried to engineer tasks where it was really critical that you use the text, like you would fail if you didn't, and tried to see how the LLM did. We could fine tune, right? There's no training on all this. Like nothing here has been trained, it's just out of the box. We could try fine tuning the model a little bit. There's a bit of a balancing act there where you don't want to, like with any fine tuning, you don't want to like train out any latent knowledge that the model might have. Like I have no doubt that if you just take the architecture of an LLM and like train it on a lot of data, it will do regression, right? Like we know that. But will you ruin its ability to condition on text? Right, so again, talking about the flexibility of the encoding scheme. So we can model categorical data, and numerical data. We can do joint distributions of those two types of data sets, right? It's incredibly flexible, mixed data types, images, toss them in there, right? The world's our oyster. Automated prediction on tabular data, and I'm working on looking at some economic data. So like taking economic indicators, maybe like news articles, things like this, tossing it in, trying to do some forecasting for the Canada Food Price Guide, or looking at medical data, right? Doctors' reports, things like this. Can we just like toss them in and do better for regression problems? So open it up for questions now, or if you guys have any ideas like you want to toss at me for things to look at, that could be cool. Thanks a lot for listening, and thanks for inviting me.
Thanks for the great talk. I actually have a question about one of these that you have here. So using it for categorical data or taking like factor type variables and how you transform them. I'm curious, like say you take a factor and you want to basically transform it into a bunch of binary type variables, how important the way you like call them or name them is to this problem when you're modeling with a language model. So your choice for taking a factor variable that may have multiple levels, and then how you choose to then name the binary variables for each of those levels. How does that affect this?
Yeah, that's a really good question. I would think that there would be, my guess would be there would be cases where it is important. My weak evidence for that is when we did the housing price example, all we did was we took the numerical data and we labeled it. And our hypothesis is that the label was able to tell it how it needed to, what the relationship was between the numerical value and the thing it's forecasting. And so in the same way, my question about if you transform, like if you did a transformation of the Y values, you'd be destroying information because it wouldn't know about it. I think if you just take categories and you give them like random arbitrary like numbers, then it's going to be confused or whatever. So I think in certain cases, like, or if you're, if you give it like, maybe if you give it even the opposite direction, overly descriptive, like, you call the top thing like really crazy out of bounds or something, like, that it might place a lot less mass on that, right? So I don't have an answer, but I would think that there's a lot of engineering that would need to go into like choosing good things. Yeah, that's a cool idea.
Yeah, thanks for the great talk. Just something that I kept thinking about when we talk about bias, I would imagine in the training set, extremely large numbers are less likely than small numbers. And it looked like a lot of the regression tasks and things that you were doing were in the sort of small number regime. Have you noticed that the model's either rounding or less accurate when you're asking it to do the same kinds of computations, but with just large values?
Yeah, so definitely noticed an integer bias, or like a bias to like kind of end the value. And that might be part of the explanation as to why when we took the same task and just scaled it up, it did worse.
Okay.
So if you like, it's better in terms of performance for those kinds of things. And then,
So wait, just so I understand,
Yeah.
the exact same task, but instead of multiplying 3-digit numbers, you're multiplying 6-digit numbers. or something
exactly.
like this. Okay.
Yeah, exactly. Yeah. Or like
Yeah.
you just take all your values and multiply by 1,000. All of a sudden, its error is gonna be worse.
I see.
Even like measuring for like normalizing there. Yeah.
I see. And it's not clear whether that's a data distribution issue or the numerical stability issue that was raised earlier.
It could be a numerical instability issue, like in that you're rejecting a lot. Yeah, I don't know. I don't know.
Yeah.
It's hard for me to think that would be a numerical instability issue, but it could be.
Okay.
Yeah.
Yeah, thank you.
Thanks. One thing that I wonder to your point, well, it's related, but I wonder if there's a funny inference bias in it, in that how the order of magnitude for things might be a bit strange. In that, if I tell you the price of something is 50, right? Okay, 50 what? 50,000. So sometimes one more token just blows the whole thing up. And if you generate digits one by one, I would expect that sometimes you're like, whoops, I added a zero, and then the whole thing blows up. So are you more, okay, so do you like optimize the mean square error in log space instead of the mean square error in the original space? Is there such a, I mean, have you, I mean, I'm not sure how to ask my question, but is the magnitude sometimes completely off because, oops, an extra digit slipped in? It slipped in, I mean.
Yeah, it's potential. So it has to, we do look for the terminal token. So we reject anything that doesn't actually say that it's finished. So it can't, like, it can go off the rails, but it has to be like, start adding like digits and then put a terminal token. And then like, at that point, it would like blow up the error. So that's entirely possible. So I'm trying to get to the crux of your question. Can you repeat it just again?
Well, so I mean, I'm thinking about it in terms of Benford's law, almost like when you have a bunch of stuff and the magnitude isn't known, like number of bags of Cheetos in this room. You're like, well, I don't know, is it 10,000? Is it 3,000? Is it 4?
Yeah.
So the order isn't really set. So I wonder if this thing is also confused in terms of orders of the output. Like you add one more digit and the whole thing goes up by tenfold. So I wonder if there's a certain inference bias in your predictions, in that it tends to sometime get the order of magnitude completely wrong, or if this doesn't happen because it generally tends to stick to the same number of digits.
I think it generally tends to stick to the same number of digits. If I were to explain it, I would say like, so let's say you have some problem and its order of magnitude is like in the tens, and it's already output like 3.5, right? Then it's true that it's like, oh, your error is going to go way up if you introduce another digit that's not the terminal, right?
Mm-hmm.
But it also, if it's a good model, it's also going to put a lot, because it's conditioning on the fact that it's already output 2 digits. If it's a really bad model, then it'll put another digit. If it's a good model, it'll know like I have to stay within this order of magnitude, right? And so it'll be really unlikely for it to like toss another digit in there. That would be my guess.
Okay.
Yeah.
Thanks for the great talk. Earlier, you were comparing the LLMPs to GPs, and you were saying that they were competitive. But could you explain in what sense they're competitive? Like, for example, do you think the LLMPs would perform well, for example, for regret minimization in a contextual bandit? It looked like the uncertainty estimates were quite a bit lower than the GPs.
Yeah. So competitive, let me put a little asterisk there, because we compared them against squared exponentials. Okay. Like I think that if you did a lot of kernel engineering, like you really looked at your problem, you did a lot of kernel engineering for that particular problem, then you could probably like get a lot better results, like tuning your GP. But just like vanilla, like not actually encoding any like prior information, just saying you're using a squared exponential, it had a lot better log likelihood values. So it was like better calibrated in that sense on the test set. It was competitive, like as good or better generally. That's what I mean by like competitive. And then having said that, I really like, I want to highlight the fact that I think that these models, their use case is really like when you want a condition on side information. It's like you have something else that you want to toss in. Otherwise, like, I think you're better off just using a GP or some other regression model that, you know, probably would be better suited for the task. It's gonna be way faster and cheaper, right? So,
yeah. I mean, like it sounds like it could be really useful for like contextual bandits, though. Like if you have some natural language context.
Yeah.
But okay, so you're saying you're evaluating it just on the log likelihood of
Exactly.
of the test set and not on like some distribution on
That's
functions
right.
or something. Okay.
Yeah. And I mean, the other sort of weak evidence we have is like we looked at like iterations in a Bayesian optimization setting against like some out of the box like optimization algorithms, and found if you use, I think it was like, might even have been Thompson sampling with our method, we're as good or better as like the out of the box method. So it has good, like pretty good uncertainty estimates, like in that sense.
Yeah, really cool. Thanks.
Okay, we have a question online. Tegan, you can ask your question.
Hey, James, it's Tegan. Good to see you. Thanks for a great talk. You sort of answered part of my question in the previous one, talking about uncertainty estimates, but I was just curious to hear more of your thoughts on getting uncertainty estimates out of like LMPs and calibrating those uncertainty estimates.
Yeah, I mean, we did zero work on like we just let it fly, and we just tried to see like how measure its log likelihood or its performance on Bayes-op, and compared to like something like GPs, which people claim have really good uncertainty estimates. And so preliminarily, we were super impressed that it was able to do so well. I mean, and as I showed before, it has weird artifacting, which maybe is not like super representative in the log likelihood. And if you don't want something like that, you might be a bit scared of this thing. At least on our test sets, it seemed to perform pretty well. And we're looking now at fine tuning a little bit. Like, can we actually calibrate these things a little bit better on a particular task if we wanted to perform better on one particular thing? But that's the extent of what we've done in that direction.
Cool, thanks. There's some interesting climate work that I'll try to dig up about calibrating uncertainty estimates from like small sets of real measurements. Yeah, I don't know, I can imagine that being
that could be cool. Yeah, that could be a really cool objective to say like, okay, I care about that. Let's do a little bit of fine tuning. Can I improve it in that direction on that task? Thanks.
Exactly. Yeah, I was really I was doing conditional generation with like LSTMs, but way before we had LLMs to do this kind of thing, and I don't think we could have done it with things like pen data examples.
Yeah.
But yeah, I think these work pretty well.
Cool. Thanks.
And Omar is asking if you think that something like chain of thoughts prompting can help improve the predictions.
Yeah, that's a super good idea. So we thought a little bit about it. One of the questions is, so let's say you want to do chain of thought. It outputs a predictive distribution. You want to tell it about its predictive distribution and say, can you improve it in this areas? And one of the gotchas that we have to think about is like, how do you actually get its predictive distribution, encode it back into text and put it back in? Because right now we like get either a bunch of samples, like the representation of the predictive distribution is a bunch of samples, right? Or like a histogram essentially. And then we have to like tell the LLM about it. One debate that David, my supervisor, and I are having is like, does it make sense to actually have predictive distributions as a dedicated modality for LLMs? We've now demonstrated it as a capability, right? It can do probabilistic regression. Let's actually like build a regression head onto this thing and parameterize it in some way. And then if you have that, some like representation, then you could plug it back in. You could of course ask it to like, we haven't done any experiments asking it to like tell us a parametric form for like a particular task, like give us the Gaussian mixture model parameters or whatever, and then you could do chain of thought. But yeah, it would be really interesting to do something in that direction.
All right. Any other question? We are right on time. So let's thank again James for the talk.
Thanks, everybody.
And I'll stop the recording.
I'll end it. Yeah.
Yeah.